Thank you, Don.
Okay, so as David said, I'm with ARM. I'm in ATG, which is the Architecture and Technology Group. Our job is to look 3 to 5 years out. Product looks before that, and research looks beyond that. So we're somewhere in the middle of that. What I'm going to be talking about is the evolution of TrustZone, what we're doing, what TrustZone will look like next iteration. This is all public data. Nothing here is non-public. There's a reference at the end that is a reference to a white paper that discusses this in somewhat more detail. There's also other stuff you'll find on the public website about TrustZone if you're interested. I guess I should go back. So the two topics here are the introduction of SEL2 in the hardware architecture, which is secure exception level 2 for secure environment with software around or firmware around that to support that new mode and the rest, and a bunch of other things actually. It's called secure partitions. So a quick overview, just to make sure we're all on the same page. So TrustZone is a hardware isolated, sometimes called trusted, secure world. There are various terms. They're all the same. They're all interchangeable. And the normal world or the non-trusted world. Secure hardware resources are only accessible from the secure world while running in the secure state. It includes memory, software, any bus transactions, interrupts, and peripherals. So you can attach secure peripherals to TrustZone as opposed to the secure world as opposed to the normal world side, and they're only accessible from the secure world side. Same is true for all the other resources. What haven't I covered here? So it provides confidentiality and integrity for secure assets. The whole idea is to separate the assets between the secure world and the normal world so that the secure assets, like keys, for example, are not directly accessible by the normal world. They're only accessible via secure services by invoking the secure world services, which are typically implemented in what's called trusted applications. I'll show a bit of that later. One of the important points is that TrustZone runs on each application processor. So the application processor is split by hardware into the secure world and the normal world, but each application processor independently runs code in one world or the other at the same time. There's no dependency between processors, except of course if you're using a serially reusable resource and you need to somehow serialize that within the code executing on the secure world side, and there are ways to handle that we'll talk about in a minute. You can think of the invocation from a software standpoint like an SVC or an HVC. It's called a secure monitor, called an SMC. What that does is cause the secure monitor, we'll show the stack in a minute, to get control when that's issued, and you're now executing in secure mode. It's a highly architected set of registered content that's associated with the SMC, and that allows the monitor to correctly route and dispatch the request to the right trusted OS and the right trusted application. Oh, one other point on there is, I think that's probably clear at this point, but it's not like SMM. When you issue an SMC, it's only local to that processor. All the other processors continue to execute whatever they're executing. There's no interruption or disturbance of the other processors. And we're talking about V8A here. There are changes for M class, but I'm not going to talk about those today. The programming model, execution model for the secure world is that it doesn't act independently. It only acts on request either via SMC from code or secure interrupts or some other hardware events. It's not intended for whole applications. It's intended for secure services that you've abstracted out of the applications you're running, and you implement those secure services in the secure world. They get control, perform whatever service it is, and return the result to the normal world through shared memory mechanisms. So one of the things about the SMC architecture that should make this a little more clear is it only supports two types of calls. One is the fast call, and the fast call essentially emulates an atomic operation, runs to completion, and returns the result. The other is the yielding call. The yielding call runs until it's got any interrupts enabled, and runs until it gets an interrupt or decides it needs to yield. It then yields control back to the normal world by returning. It returns along with that a return code that says, hey, I'm not finished. Give me control back when it's convenient. And when that thread in the normal world gets control again, there's no guarantee it'll continue. When it's dispatched to the normal world, it goes back through the hypervisor and the OS or whatever layers of software in the normal world. When it gets that thread in the normal world gets control again, it'll look at the return code and say, oh yeah, so I need to reinvoke secure world. It'll just reissue the SMC. The secure world will understand that's a continuation and will continue until it finishes. So there are some long operations that need to take place in the secure world, but they're taken care of by the yielding call and the mechanisms available to do that. So we'll quickly look at SEL2, or we'll look at SEL2 and secure partitions, but first I'll try to explain where we're coming from. Many of you are probably already familiar with this. The pre-8.4a, 8.4 is the dot level of the architecture that describes the new SEL2 functionality, and then on top of that there's a lot of additional software that attempts to, that not only implements the functionality for SEL2, but attempts to make a lot of the current software that runs both on the normal world and in the secure world to support the functionality. It provides common mechanisms for communication, for instance, and for execution that don't need to be replaced individually for every different application, which is the case currently. So one of the rationales for this extension is that the current model was pretty much used by either low-end devices or handheld devices, cell phones, etc. And they were, for the most part, dedicated devices. As you grow towards high-end server devices with highly virtualized environments, with VMs or other structures of application that don't trust anything else in their environment, and you want to implement secure services to protect your secrets, you don't want them implemented next to somebody else's secure service that protects its secrets, or you don't want it implemented next to, for example, manufacturer-provided firmware. You want to isolate those. So that's the justification, or one of the justifications for going from the current architecture to the newer architecture. There's a couple of things I should explain about this picture. So the current architecture has 3 different exception levels in the normal world. EL0 at the top, that's the user mode application space. EL1 in the middle, that's the OS kernel space, and then EL2, which is the hypervisor space. EL3 is at the bottom of the stack, and it's the most privileged level. It manages the transition between the secure world and the normal world and back. It also dispatches requests from the normal world up to the trusted OS which then dispatches that workload to the appropriate trusted application, which returns back through the stack, and the hypervisor and the OS kernel get to decide what to dispatch next in the normal world. I'm turning away from the microphone. Can you still hear me when I'm talking? Or am I mumbling into that? Good. Okay, good. So there are three other things I should mention about this environment. One is that this environment, the secure world environment, is established via verified boot. So at power on reset, a ROM copy of the first boot load image gets control. It then uses a key, so it's the hardware root of trust. It has also a key in OTP that it uses to verify the second load of boot, which it loads and verifies, transfers control to if the verification works. That is continued up through the various loads of boot, up through establishing the, in this case, a single OS trusted kernel and the TAs, the trusted applications. Then execution is transferred to the normal world using UEFI or U-boot or some other boot mechanism that then instantiates the normal world. The second thing to mention is that the memory protection that's in place is established by the secure world during boot. All of the memory that belongs to the secure world is not mappable by the normal world. It's entirely protected. There's a bit in all transactions on all buses, as well as for example, memory addresses in cache called the NS bit. So it's a little bit backwards. It's the non-secure bit is 1 when it's non-secure. It's 0 when it's secure. If your transaction is non-secure, it can't touch anything in the secure world. On the other hand, the secure world can touch things both in the secure world and the normal world that allows things like sharing memory for communication, for example. Devices can also be attached to the trusted world, and those device transactions then are completely secure. That device can't be accessed by the normal world. The other thing to mention is all of this code, all of the firmware is open source. It's currently open source and it will continue to be open sourced. So the intent is that OEMs and other platform manufacturers can modify the code as needed. It'll still need to be signed by a valid signing authority. It'll still need to pass verified boot in order to boot successfully and instantiate the system. So the verified boot ensures A, that it's from a known source, so it's authentic, and B, it hasn't been modified before it's loaded. There are, as we talked about in larger systems that are highly virtualized and multiple different, essentially independent clients, probably belonging to different organizations, there needs to be additional separation. There isn't that separation currently in the secure world, so the principle of least privilege isn't really carried out because, for example, EL3 and SEL1 have the same access. They're both privilege levels, but they essentially have the same access. EL1 can access EL3 memory. EL1 can access all the normal world memory. So there's no separation there. So any infection, any bug in EL1 code, the trusted OS code, can affect both the secure side and the normal world side. So the other issue there is that other TAs belonging to separate entities can't be separated or isolated one from the other, given the current structure. So the introduction of SEL2 is intended to provide that isolation, both for DMA access, memory access, and device access. Along with the firmware /software that's being provided, it provides a common runtime environment for the software, both on the normal world side and on the secure world side. So there's a quick picture that's somewhat like the previous one of what happens post 8.4. The Secure Partition Manager is introduced as a very lightweight hypervisor. It's not a hypervisor in the traditional sense. It doesn't individually schedule VMs. What it does is provide address space separation for multiple instances of trusted OS and trusted applications in this world. SEL1 now is prevented from accessing anything outside of this box. So it can no longer, SEL2 didn't exist, no longer access SEL3 resources, nor anything directly that's not mapped via the call mechanism.
I'll give you a look.
Okay.
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 So you can clip that. Now you can move about.
I can wander.
Yeah.
Nobody was complaining. Either they weren't interested or it didn't matter. Boy, that probably turned that down a bit. Yeah. So the isolation is provided by both the introduction of SEL2 and the introduction of software that's called Secure Partition Manager. The SEL2 world virtualization provided by Secure Partition Manager, it provides, as we said, the hardware isolation between software components. It removes the need for mutual trust. So now everything can be individually packaged and delivered just like it is in a VM. VM, for example, on the normal world side, only much simpler. It can be packaged. It'll also be verified at verified boot time when it's instantiated in the secure world. SEL1, again, is each is a compartment. One SEL1 instance is separate from and protected from every other SEL1 instance. One of the important things in terms of development is this allows independent development. There's no integration phase. You can independently develop and audit what is running in your VM/secure partition. And you don't have to be concerned with what's running anywhere else. Whereas in the previous instance, everything had to be merged and there had to be an integration phase, and you had to make sure that everybody ran in a mutually beneficial way within that address space. That no longer is an issue. So Secure Partition Manager, and we'll see a slide at the end that illustrates this to a greater degree, provides APIs that allow various vendors and different parties, third parties at various points in the chain, including perhaps somebody who offers a platform as a service function to actually instantiate their customer secure elements, secure code on that system in a secure way, secure manner. Standardized communication, we'll see that in a little bit, and it removes, importantly, it removes what is currently vendor-specific code in EL3 and EL2. So EL3 and EL2 being the most trusted levels of execution of the system, currently have to have vendor-specific code implemented in order to make all of this infrastructure work. That is removed with the introduction of SEL2 and secure partitions. So the Secure Partition Manager is the name of the chunk that runs at SEL2. The VM is referred to as a secure partition, which has isolated address space. The hosted trusted OS and or SIP stack driver is, for trusted hardware, is also isolated in an SEL1 environment. And the Secure Partition Manager provides, we've already said, generic code for EL3. So it's got some code in EL3 as well as some code in SEL2. SEL2 is the major part of the code. And it runs, most of it runs and dispatches and manages the secure partitions in the SEL2 piece of the code called Secure Partition Manager. So there's a, I'm actually going to finish on time. So there's a picture that tries to show how the software is broken up and becomes generic in several senses. So the yellow stuff along the top is all application specific. So the client application, or CA, and the trusted application, or TA, are bound and in some way specific to that application. The TA library, client library, are opposite ends of the chain. The Trusted OS driver and the Trusted OS kernel are opposite ends of the chain. The resource description is a mechanism that says what resources are allocated to this particular secure partition. There is the provision for vendor-specific implementations for platform firmware to initialize and otherwise manage platform-specific hardware that a vendor. So you all know that ARM is an IP company. We essentially allow others to use our IP for a penny. And they, in fact, we call them SIP silicon providers. They, in fact, provide the processor. There are other people that may build platforms from that. And so ARM is right at the beginning with the IP. They don't control the implementation of the actual SoC, which typically also includes vendor-specific hardware that surrounds the processor. So there may be specific implementations here for that vendor that initialize and manage its specific SoC devices. But the dark blue boxes here are what becomes common code, which in the previous instantiation was not common. It was all custom and related to the application. So there might be multiple occurrences, just as there are here, but they all be application specific. Formerly the EL3 firmware knew by the information in the SMC what to dispatch. It still knows that, but it uses a secure partition manager to decide how to do that and to map those addresses. So just like stage 1 address translation here takes place here, stage 2 takes place here to get a physical address. Stage 2 takes place here, and stage 1 takes place there. So you still have the stage 1, stage 2 address mappings that are managed by the different layers in the stack. This is the penultimate slide. This is an attempt to show a cartoon of the secure partitions software model. It includes something called the Secure Partition Manager, or SPM, the Secure Partition Client Interface, or SPCI, the Secure Partition Runtime, or SPRT, and the Secure Partitions, which actually implement the functionality that's needed for the applications. So the Secure Partition Manager is, as we've seen on the previous slide, highly privileged software that manages all the secure partitions. So it's responsible for individually managing what those partitions can get access to, what they can see when they execute. Conceptually, it's similar to a hypervisor managing guest OS, but it's much, much simpler. And it only gets executed on demand. It doesn't individually decide when to dispatch anything. TFA, sorry, that's an acronym. Trusted Firmware A provides a reference implementation for all this, and we'll continue to do that and that will be open sourced. The current version is in GitHub. Subsequent versions will be in GitHub as well. There's a common runtime model that's propagated with Secure Partition Manager. That SPRT you see is between essentially what's SEL2 and SEL1 in the Secure Partition. That runtime is defined and common. And SPCI provides a common interface from the normal world to the Secure Partition Manager and up to the Secure Partition. So formerly stuff that was bundled in the SMC only and had to be understood by the most secure level of software at EL3 in order to dispatch, that's currently handled by the information in the SPCI packet, and that now can be managed in a much simpler form. So the common runtime model is client-server based, at least in some senses. The server is the secure service in the secure partition, and the client is either a normal world client on that side, or it can be another SP, which can access it internally via an SVC. So an SVC issued by a secure partition will be cut by the Secure Partition Manager and then will be dispatched into either another TA or another secure partition to carry out the work, and the return will take place in a likewise fashion. It'll unwind. Standardized communication, we've talked about that, SPCI. It's implemented by the Secure Partition Manager. It provides discovery services. It establishes a communication channel, double-ended communication channel with a secure service. So something on the normal world to a secure service on the secure world uses SPCI to manage that. It can also manage shared memory between the secure world and the normal world. The secure world, however, doesn't share secure world memory. The normal world can share normal world memory with the secure world. And the secure partition runtime is implemented by SPM. It's available as previously via the SMC, or as we talked about, an SVC internally. It allows secure partitions to retrieve client requests, send responses back to a client in a secure manner, and receives interrupts that are targeted to it. So previously interrupts came in and they were all on the secure side, but they weren't funneled in a secure way. It also provides a common programming model for all the secure partitions. So that's it. One more slide is just a reference you can follow. That's a white paper on all of this. There's also a lot of other information on the public site that you can get at with regards to TrustZone and what's implemented there. Any questions? Yeah. Okay. For me?
Oh.
That one?
Okay.
Yelling is fine with me.
Okay, it's a simple question. So I'm glad to see Arm now that enables via software this secure partition manager and breaks that division between secure and not secure. And so my question is very simple. Why do we need to keep the normal world there and we just have everything secure?
Well, obviously not. I mean, the whole purpose of the secure world is to provide very simple mechanisms that run for short amounts of time and can be more easily trusted because they are only small amounts of code that implement simple, or at least more simple, functions and well-known functions. And an example might be crypto. You might have a crypto library that's implemented on this side that, for example, will hide the key on the secure side, return a handle to that key. Future crypto operations will only use the handle. The normal world will never see the key in the clear. So you can't do that. You have to separate all of those resources between two worlds in order to provide a reasonably well-defined and trustable entity on the system.